So we want to look at energy. We want to have a way of talking about how much energy is being used or created during some exposure. So here's the thing. X-rays are electromagnetic waves, like visible light, like radio waves, like microwaves, but different in their energy, different in, not to give you too much, but different in their wavelength. Okay? They carry more energy. X-rays are energetic, more energetic than visible light and even ultraviolet. There's a formula that we can use to calculate how much kinetic energy some object has. Okay? We're going to use it right off the bat to give you kind of a complicated formula, but then I'll give you some easier versions with more everyday objects. But here's the formula. Kinetic energy is equal to 1/2 times the mass times the velocity squared. Okay? So what really matters here is that there's some object, it has a mass. What's mass, by the way? Not MAS mass, but what is MASS mass? Like, what's it mean to have mass?
Volume.
You take up space, you occupy some volume, right?
How much volume that's in the object?
It's not how much volume that's in an object, it's how much volume does the object occupy. Okay? Anything that is matter, that is a matter particle, has mass and occupies space. It takes up some volume of space and it has some mass. All matter has that. Mass is how much stuff you're made of. Okay? Mass is not weight. Weight and mass are different. The unit for mass is the gram or kilogram. The unit for weight can be anything, pounds or kilograms, depending on what system of measure you're using. There's a conversion from kilograms to pounds, 2.2 pounds per kilogram. But the point is that mass is an amount of stuff you have. Okay, we measure that in grams or kilograms, or milligrams if it's small stuff. Velocity is how fast you're traveling. Okay, the unit for velocity is meters per second. You notice that velocity is what we call a derived unit. Okay, you need to know two things to know a velocity. Okay, you need to know how far something is traveling and over what length of time we're measuring that distance. So we need distance and length. Sorry, distance and time. Distance and length are the same thing. Distance and time. Okay, so velocity is distance times time. Okay. Like your cars, when you drive on the freeway, you drive 65 miles per hour, right? In this case, we're not going to use miles per hour. We're going to use meters per second. Okay, that's the better unit. That's the more fundamental, correct unit to use. You can convert meters per second into miles per hour, but I just don't care about that right now. It's not important to this talk. You're just going to need to learn to operate in the metric system. Okay, meters per second and kilograms are our units that we're going to work with here. Okay, mass is in kilograms or grams or whatever, but kilograms. Velocity is given as meters per second. Once you're in those fundamental units, then you can just work through the equation. You don't have to do any funny conversions to anything. You need to convert into those units before you do the equations. It's a pretty simple equation. It only has two variables in it. Okay, go ahead.
So the KE that equals kinetic energy, and then the M is for mass velocity.
M is mass. So what this really says is kinetic energy is equal to 1/2 the mass times the velocity squared. Okay, so there's a little multiplication happening between here. They don't show that because they like to make things small, compact when we write down formulas. You guys learned in math, right? We could, when we were learning how to multiply things, right? We could have said mass times velocity squared. But don't ignore the squared in half right now. We could have said mass times velocity. They could have done that. That also means multiplied. Or they can just say mv. Okay. All three ways to write it are the same. Why don't we use the x as a multiplication symbol? It wastes space, but more importantly, what is x used for? Sydney? It's a variable. X is your variables in equation. So what this looks like is, it looks like you're multiplying mass times some unknown variable times velocity, right? So we don't like to have those x's when we don't need them, when they're not being used as a variable. So we don't use x as a multiplication symbol in higher level math, okay? When we're in like grade school doing just multiplying two real numbers together, we use that x for multiplication. We just don't when we're adults. We get rid of that. So then you could say mass times velocity with a little dot, but that also takes up space, right? So you don't do that. So you say just mv. That's implied to mean mass times velocity. Okay, but again, formula is 1/2 mass times velocity squared. M is mass, v is velocity. So let's work through one of these. This one gets a little complicated. I'll try to give you an easier one, a couple easier ones with real world things in a second, but let's work through this. So this one unfortunately uses a lot of scientific notation. If you're not used to scientific notation, this can seem a little difficult. I'll do my best to make this easy for us. Okay, the first thing we want to do is we want to know what's a mass we're going to use for the formula, right? The mass of an electron, a single electron. We're going to figure out with a single electron, given its velocity, how much energy is there in that thing traveling that fast. This velocity first. So the electrons we send from cathode to anode, there's a cloud of them, a bunch of them. We're considering just one of them right now. And this one happens to be traveling at just over half the speed of light. The speed of light, where's it shown on here? It's 3 × 10⁸ meters per second. There it is. So this is the speed that light travels. It's not instant, okay? When you turn the lights off, go turn them on, it took that light some time to get from there to you. There's distance between the light and you, right? Light travels at 300 million meters per second, okay? So it doesn't take the light very long to get here. The light could, in 1 second time, be 300 million meters away, okay? So it travels really fast, but not infinitely fast. 300 million, expressed in scientific notation, is 3 × 10⁸ here. But we're not traveling the speed of light. Okay, these little electrons that we send are not traveling at light speed. Guess what travels at light speed? Light travels at light speed. Other things in principle do, but here's a trick and a key. Not a trick, it's just something to know. Anything with mass cannot travel at light speed. It cannot get there, okay? It has to do with Einstein's relativity, which don't go there. Okay, anyways, so we want to know how fast is the thing traveling. So we take the speed of light, and we say it's traveling 56% the speed of light. So the speed of light times 0.56, which is taking speed of light, multiplying it by 56%, 0.56. The answer happens to be 1.68 times 10⁸ meters per second. That's our velocity. That's our v for velocity, okay? And so we have how fast the thing is going now, okay? Half the speed of light, 56%.
So, c, just to clarify,
yeah.
c is the speed of light.
C, when you see the little lowercase c in any equation, that's saying that number is the speed of light. Okay, so like E equals mc squared, right? Everyone knows this formula. E equals mc squared, right? There's your c, that's the speed of light. So the number you plug in there is 3 × 10⁸ when you actually work that formula out. When you don't, but if you were to. Anyways, yeah, so we use c. The c stands for constant because speed of light doesn't change.
What you have in or circled up there, what was that? Was that velocity?
This is your velocity.
Okay.
Meters per second. Okay, so then we want the mass of the object that we're talking about going really fast, okay? They just give it to you. The mass of an electron is tiny, right? So it's not a whole kilogram. It's not even close to a whole kilogram. It is 9.1 × 10⁻31 kilograms. That means take the number 9.1 and shift this decimal point 31 places to the left, okay? So you're going to have that many zeros in front of the 9, okay? Meaning you have an extremely tiny number. And it would just take us a long time to write out that tiny number, okay? So we compactify it and we write down 9.1 times 10 to the negative 31. Shift this decimal point 31 places over, and you have the size, or you have the number written down, yeah.
I'm sorry, can you go over the part, it was the 3 times 10 to the 8th power? What
Yeah.
was that? What did that,
Good.
or what was that? No, it's C. Okay.
So 3 times 10 to the 8 meters per second is the speed of light, which is given as just c. So we say 56% of c, okay? So they take that number and multiply it by 0.56, okay? So if you want to do this, if you want to multiply a number in scientific notation, okay? If you want to multiply a number in scientific notation, you don't mess with the exponent, okay? What you do is you take this number and multiply it by the number on the left side, okay? So 3 times 0.56. Then you should get 1.68 when you do that. Okay, so that's how fast we're traveling. We have a mass of this, 9.1 times 10 to the negative 31 kilograms. So the formula looks like kinetic energy equals 1/2 times 9.1 times 10 to the negative 31 mass. There's your m. And your velocity is 1.68 times 10 to the 8 meters per second. And you square that. What you come out with after that, again, I'm not going to make you do these, okay? But I'll give you some easier ones that are a little bit easier to digest. But when you do that, when you come out of this, you get 1.284 times 10 to the negative 14. That's the answer to what is all of this calculated out, come out to, okay?
Joules is the amount of energy.
Joules is a unit of energy.
I'm moving.
1 amp through 1 ohm over 1 second, yeah. So don't worry about it right now. So I'm not. So we will have a section where we talk about some other units more explicitly, but right now we'll just use it. The unit for kinetic energy is the joule. Okay, joule is an amount of energy. It can be used to talk about electric energy. It can be used to talk about kinetic energy. It can be used to talk about mass energy. You can say in some object just sitting still, not moving, how many joules of energy is there if we converted the mass into pure energy? Okay, so joules is just a unit of energy. Just accept it as a unit of energy like any other unit, like meters and seconds and things like that. It's a unit of energy. So when one electron is traveling at 56% the speed of light, we can say that it has 1.284 times 10 to the negative 14 joules of energy. If you wrote it down, we would write 1.284 and shift the decimal 14 places over, 14 places that way, okay? Put the decimal point down and you'd have the number written out, okay? Very small number. It is 1/100th of a trillionth of a joule. Okay, 1 trillionth is 10 to the negative 12, so 10 to the negative 14 is 100th of a trillionth. So it's a small number. You don't need to know what the number actually is written out because you're told what it is, right? 10 to the negative 14. Okay. So there's a way to now ask, given that you have figured this out, you know how many joules of energy are in that single electron, how much kinetic energy it has. There's a way to go, all right, given that much kinetic energy, how much kV did it take? Or how much kV was necessary to accelerate it that fast, okay? So you can ask that, and when you do, you need to know how much energy is in 1 kV, okay? So here's 1 kV. In 1 kV, there are 1.6 times 10 to the negative 16 joules. Which is a bigger number? 10 to the negative 14 or 10 to the negative 16?
14.
So who thinks 10 to the negative 14 is a bigger number? And why?
It's less zeros to the left.
Yeah, this number is closer to 0 on the number line than negative 14 is closer to 0 than negative 16, right? So negative 14 is a bigger number. How much bigger is 10 to the negative 14 than 10 to the negative 16? Ignore, just for right now, ignore that.
Just 2 decimals.
2 decimal points. What's 2 decimal points worth? 100, right? Each decimal point is worth 10. 10 times 10 is 100, right? So this number here is 100 times bigger than that number, okay? Meaning that we have more than 1 kV's worth of energy. We know just looking at it without doing any number calculation, we know we've got more than 1 kV's worth of energy, okay? All right, so this is a division, by the way, right? So I will show you a little bit about dividing with scientific notation. It's not as hard as it seems, okay? The way to work with scientific notation, multiplication or division, is to work with, basically split this in half, okay? Do something with the left side and do a different thing with the right side, okay? On the left side, you have 1.284 divided by 1.6. Just plug it into the phone and see what you get, okay? Would you guys humor me and plug that into your phone? 1.284 divided by 1.6. Good. 0.80. You've got the left side of the answer. Okay? Now to get the right side of the answer. When we divide in scientific notation, we subtract the denominator from the numerator. Okay, so it's 10 to the negative 14 minus negative 16. 10 to the negative 14, minus 10 to the negative 16. Okay? Just do this. Negative 14 minus negative 16. Double negatives get turned into positive. So negative 14 plus 16 is 2. Your exponent is 10 to the 2. Okay? So in scientific notation, when you're working with it, by the way, the top and bottom both have to be in scientific notation for this to work. You can't have one in real number written out and the other in scientific notation. Make sure they're both in scientific notation. In division, you subtract the denominator from the numerator, okay, on the exponent. On the real number side, you just divide, okay? And it's you have to approach it, once you approach it operationally, one side then the other, it becomes easy, right? You get your 0.80, and then you get your 10 to the 2, and your answer is 0.8 times 10 to the 2 kV, okay, or 80 kV, okay? 0.8 times 10 to the 2, that says shift this decimal point 2 places to the right. 80. Okay? Questions here? Yeah?
Not on there, but it's going to be on this.
No, I'm not going to force you to calculate velocity. The point here is to show you that there is a formula. You can calculate how fast something is traveling, right? You can calculate what its mass is, and given those two numbers, you can know the kinetic energy of something, okay? Let me give you I was toying around, I was bored last night when I was at home reviewing, so did a couple of these just to kind of play with it, and let me give you just a couple, okay? They might be interesting. Okay. Alright, so let's give a couple of these. Mass, we're going to do, I think, 2 or 3 of these. So let's give mass 1 for the first equation. We're going to say that object weighs 1 kilogram. Velocity 1, we're going to say is 1 meter per second. So you've got a 1 kilogram object moving 1 meter per second. You want to know what's its kinetic energy. Did you have a question? Sorry.
In the real world, like, you've been doing this for so long, how
many times have you had to do this?
How do you mean?
Like, you've been in the office, like, actually use these formulas and like figure things out yourself?
Well, you're not calculating the kinetic energy of your projectile electrons. The point is you need to know that your electrons have kinetic energy that can be converted, and you gotta know that there's a way to calculate it.
No, I just really wanted to know because I was nervous because I'm bad at math.
Don't worry about this and practice this to get better, okay? Do it. Take something that's interesting to you, right? Plug its mass and a velocity and ask how much kinetic energy it has. It's not hard.
I think all of us are just kind of like imagining our days on the job, sitting there doing a bunch of equations.
No, I mean, once you get out to the externship, you see what your days on the job are like, right? But if you don't have the underlying base to talk about all this from, then you're just pushing buttons, right? Not knowing what you mean. You're just a button pusher, and you don't want to be a button pusher. All right, so let's do a couple of these. I think it'll help make sense. This stuff is fun for me, by the way. All right, so let's just do two. Just do two of these. It's not that hard. So what's our formula?
I'd rather watch my.
Kinetic energy 1/2 mv squared. Okay. So let's do number one. Our mass for number one, we have a 1 kilogram object. Okay, moving at a velocity of 1 meter per second. Okay, this one's pretty easy, right? Take care of your exponent first. 1 squared. 1. 1 times a half. So the answer, 0.5 times 1 is 0.5. 0.5 what?
kg.
Not kV. The unit for kinetic energy is joules, right?
Oh, sorry, you converted it somewhere.
This is your mass. This is your velocity. 1 kilogram, 1 meter per second. So an object that weighs 1 kilogram, moving at a rate of 1 meter per second, okay, has an energy of 0.5 joules. Let's ask what a car might have moving down the road, okay? So a small car, weighs about 1,000 kilograms, okay? And moving at a rate of 30 meters per second. It's sort of an average-ish speed. It's not like highway speed. It's not like crawling. It's in the middle-ish. So let's ask that one, okay? This is number one. Small object moving slowly. Now you've got a car moving a little faster. Our mass is 1,000 kilograms. Our velocity is 30. Okay. So what should we do?
Do the exponent first.
Do the exponent first. What's 30 squared? 30 times 30? 900. 3 times 3 is 9, plus the 2 zeros. Okay, good. So 900. What's 1,000 times a half? 500 times 900?
45,000.
450,000?
Yes.
Good. So our answer, huh?
Who needs a calculator?
You can do some of this. 5 times 9 is 45. Okay. So 5 times 9 is 45, and how many zeros do you have left over? 4. So throw 4 zeros in at the end of 45, right? 45 plus 4 zeros is 450,000. You can do some of this in your head as long as the numbers are sufficiently simple. If this velocity was like 31.29, right? No way, we'd have to plug it all into the calculator, right? But in our head, we can do some of the easy stuff that has, nice, even, rounded off powers of 10 kind of numbers. So our answer for kinetic energy is 450,000. 450,000 what? Joules. So your car driving average speed down the road has 450,000 joules of energy. If you were to run it into a wall, convert its kinetic energy to 0, okay? You're converting 450,000 joules of energy into other things, heat and sound and other stuff.
You should
Okay?
play,
Huh?
you should play some videos where they have like
crash test?
Yes.
In car, and
Oh,
then
yeah, yeah.
The slower speed,
Oh,
you
I
see
love
it.
But I think everyone's seen that,
No, I
right?
saw, they have them on
No,
TikTok.
Crash test
Like,
videos?
they run into different things at different
Yeah.
speeds and
Yeah.
it shows like the damage. They're pretty cool.
So let's do one more, okay? Let's give the same car, okay? So it's your same car, 1,000 kilograms, but let's say it's not traveling 30 meters per second. Let's double its velocity. 60 meters per second. So it's 1/2 times 1,000 times 60 squared. 36,000? 3,600, that's what it is. Okay. So it is, we can do the exponent first, that's the right thing to do. It is 3,600, right? 3,600. 1/2 times 1,000 is 500. So what's our answer?
900,000.
Let's double check it. 1.8 million, right? You had at 30 meters per second, 450,000 joules. You might think if you doubled this is really good, Abby. You might think that if you doubled the speed, your overall energy would double, right? So double the velocity to 60 meters per second, and if you don't run the formula through, you might go, well, then if it was 450,000 joules, then it must be 900,000 joules if I doubled the velocity. But that can't be true because your velocity gets squared, right? The velocity counts for more than mass does, okay? So you end up with 1,800,000 joules,
So
which is
it's-
way more than 450,000.
It's that, the inverse square law.
It is an inverse
Roughly.
square, it is a square law. It's not the inverse square law. It is a square law.
The square law
Yes, it's what we call square law.
is roughly 4 times. Yeah, 4 times. Because
That's why it's a square law, yeah.
Because it's 4 times the speed. Well, it's twice the speed, so it ends up being.
Exactly.
That's where I'm going.
Yes, yes. Double the velocity, you get a number 4 times bigger, right? I said way bigger, but 4 times bigger, right?
Nobody knows what I just said, so.
So is this why like the lethality rate between like 30 and like 35 goes up like 70% if you
Yes.
hit someone?
Yes, that's why it's more dangerous at just a little bit faster, right? It's only double the velocity, right? But it's so much more, 4 times more energy in total, right? So the whole point of doing this with the same car twice, right, at 2 different velocities, is to show you that velocity counts for a lot more than mass does, okay? So in an X-ray machine, to make X-rays, what counts is not how big the electrons are, because they're small, okay? What counts is how fast they're going, the voltage that we apply, which is why we need thousands of volts, not tens or hundreds of volts. If we only had tens or hundreds of volts of oomph, the electrons would not be moving very fast, okay? And would be not making X-rays, not producing X-rays. They'd be making heat and light, right, instead of making X-rays. In order to make X-rays, we have to move electrons really, really fast, okay? So again, the whole point of this is to show you that kinetic energy is, we can calculate things with kinetic energy, and velocity counts for more than mass, okay? Beyond that, I'm not going to make you do much with this formula, yeah, besides remember it.
You had a number there, the mass of electrons, is that a constant
Yes,
number?
it is, it's
So,
one of those things.
Whether it's an electron of copper versus an electron of tungsten?
Yeah, yeah.
They have-
You can take an electron from a copper atom, go put it in in a tungsten atom, right, and it's going to be perfectly happy and at home. It's the same mass, the same charge, and the same spin. Amount of spin. Direction might be different, but amount of spin. Elementary particles have these things called these fundamental constants, right? Electrons have mass, they have charge, and they have spin. Their electric charge is -1 for our consideration, right? Their mass is 9.1 times 10 to the negative 31 kilograms, and it doesn't change. And they have some rotational spin that we don't care about because we don't work with it. But they have it, and it's there, it doesn't go away, okay? Take an electron and make it move really fast like we do, and then slow it all the way down. Once it's slowed all the way down, it still has the same mass, the same charge, and the same spin. It just has lost its kinetic energy. So it's conserved. Yes, that's a really good question. It is a conserved thing. All right, good.